Good morning, everyone. Thank you for being here. I'm excited to be here to share with you our newest chromatography resin offering. We actually launched this 2 days ago on Monday. So this is the second time we present here. So thank you for coming out for it. So we're going to talk today about the Purolite Praesto AP resin launch that we just had. Again, I'm Aaron Moulin. I'm one of the field application scientists for Ecolab Purolite resins here based in the Boston area. So at Ecolab, for the past 100 years, we've been very concerned about health, be that the health of the planet, the health of your business, or the health of people. And around that last point in particular, we're going to talk about our newest resin launch, meant for the manufacture of biological therapeutics to help with the overall health of the general planet. And with that being said, I'm a downstream guy, but our fine upstream colleagues are always making constant improvements in their processes as well. So as titers get higher, as production gets faster and more intense, that requires our downstream efforts to match and keep pace with that. With that being said, we've developed our new line of Praesto AP Protein A resins to meet that demand of high titers, rapid throughput, and also just cost efficiencies and economic efficiencies and process efficiencies. So you can see here, we're trying always to reduce costs, and I'm not just saying that we want to make the resin less expensive, which we do, of course, but we're talking about making the whole process less expensive. So improved process economics in terms of your purification strategies, your total front-to-end process. We want to make sure all of our resins that we develop at all times are easy to implement. And of course, we want to make sure that they fit legacy processes that customers are already using, especially when we're having an eye towards second-gen processes, biosimilars. We want to make sure we can just slot and implement existing legacy products and to handle all of these high-titer processes. We want to make sure that there's good technical equivalence. We'll talk a little bit more about that later, but make sure that any resin that we develop is technically equivalent or superior to current resins that are already on the market for use in bioprocessing. And the last 2 points, high capacity. We want to make sure all of our resins have high capacity and good lifetime. Those are non-starters. If you don't have a high capacity resin and a good lifetime, then there's no sense in trying to implement that in commercial processes. So our AP line, we feel, uniquely addresses all four of these issues and tasks, especially with an eye to newer second-gen processes and biosimilars, making sure to keep it as cost-efficient and fast as possible. Talking about the technical equivalence, of course, any resin that we deliver must have a technical equivalence and process efficiency. We'll talk again a little bit more about what we mean by the technical equivalence later on in the talk. But the AP Plus platform gives us the advantage that our ligands are technically comparable or better than ligands out on the market already. And the B platform that we use with our jetted technology makes this an optimal performance platform for traditional mAbs and high throughput process intensification processes. In particular, we're going to focus today on our AP plus 50 resin. So it's our AP ligand, a very high capacity, caustic stable ligand on our 50 micron jetted bead platform to offer increased capacity, increased resolution, and of course this one is ideal for process intensification purposes, and we'll talk about that. But first, let's talk a little bit about the thing that's almost first on everyone's mind. What's the capacity of this particular resin? So we have in blue here, the Praesto AP plus 50 dynamic binding capacity. So you're looking at the QB10 at various resonance times, plotted in comparison to the main legacy resin out on the market. So you can see at essentially all resonance times, the Praesto AP plus 50 will outperform the predominant legacy resin on the market. There's a particular advantage that you can see at relatively low resonance times, around 4 to 6 minutes, where you still have very, very good capacity with our Praesto AP plus 50 compared to lower capacities on more traditional resins. Even at a 3-minute resonance time, you can see that you can still get 50 grams per liter QB10 on that resin, which is really excellent capacity. A little bit more around that, just to show you how it compares to some more competitors. So again, we still have the same competitor A, and then we've got competitor T, competitor J, plotted against our AP plus 50. And you can see that at almost all data points, our Praesto AP+50 outperforms the competitors in terms of capacity. You will notice that competitor T does have slightly better capacity at very low resonance times, and that's a function of it being a very, very small bead. But it comes with its own difficulties in terms of packing and mechanical handling. But you see very competitive, very good binding capacity. And of course, we have here shown one example with a monoclonal IgG, where you can see we get a greater than 70 mg per mil capacity using our resin versus, mid 50s with the predominant legacy competitor on the market. Capacity is great and it's important, but so are all of the other process attributes when you're trying to purify molecules. So we wanted to make sure when we were developing this resin that using all the industry standard platforms, buffers, processes, that we show technical equivalence with minimal changes to any sort of processes necessary. So you can see here we're looking at yield, log reduction of HCP and residual protein A with our resin and the main legacy competitor resin, using all the same buffers and all the same sort of standard platform choices in terms of operation. And you can see for the 3 cycles that we plot here, the yield is identical to the main competitor. Log reduction in HCP also identical, if not sometimes slightly better. And the leach protein A, the residual protein A, is also as good as, if not better than, the legacy protein A on the market there. So, and this is again using all standard sorts of buffers and platforms that most people implement for the legacy resin. The idea here being that we offer an economic advantage here while not sacrificing anything in terms of the science and the operational outcomes. One last one that doesn't fit on the other one, in terms of the elution profiles, the elution CVs, so you still have nice tight elution CVs, exactly the same or better than the main legacy resin out on the market. Alkaline stability, of course, is another topic that comes up in most people's minds when looking at a resin in terms of life cycling and lifetime. You can see at our recommended cleaning strategy of 0.1 normal, which is true for all of our protein A resins, so 0.1 normal hydroxide with our AP+50, with the current data that we have in hand when making this presentation, out to 100 cycles, you can see that we still have greater than 90% capacity compared to the original QB10. And even at 0.5 normal, out to 100 cycles, we're still better than 80% of the original QB10. So if you're loading to a 70% safety factor, you won't suffer any loss in any of these experiments. So very good in terms of the legacy resins that are already on the market. Flow properties, so we're looking at a 50 micron bead here, so it's a little bit smaller, and I'll point out a couple things here. Focusing here on the sort of industry standard 20 centimeter bed height. If you're operating at a 20 centimeter bed height and you want to stay below that sort of 2 bar safety factor, your maximum linear velocity will be somewhere around 200 centimeters per hour. But if you have the flexibility to reduce those bed heights all the way down to 10 or 15, you can achieve much faster linear velocities, so as much as 375 or so at a 10 centimeter bed height, and 275 or so at a 15 centimeter bed height. And we'll show you the benefits of doing some of these shorter bed heights and faster flows in terms of process economics in some of the later slides. Talking about process economics, a lot of that is driven now by process intensification. So there are multiple different ways to intensify processes. When talking about downstream chromatography, most people sort of focus on a handful of them, 3 of which are shown here on the screen. So one of them would be the multi-column parallel batch, which is sort of a flip-flop mechanism. So it's not exactly multi-column chromatography in a continuous fashion, but you have 2 columns, one that's always in the loading zone, and then one's experiencing all of the non-loading steps, wash, elution, regeneration, and you flip-flop those functions over time, so you can have smaller columns and greater resin utilization. Then there's, of course, the traditional multi-column chromatography, be it a PCC, like a periodic countercurrent chromatography, or an SMB, a simulated moving bed. But the idea being there that you usually have 2 columns in the loading zone, one which is experiencing primary loading, one to capture the breakthrough, and then another or 2 other, maybe more columns that are going through non-loading steps, washing, elution, regeneration, and then you cycle those columns through the various functions so that there's always constant loading and you maximize binding capacity. And it never stops, hopefully. And then, of course, there's just rapid cycling, small columns, short bed heights, where you just run faster in binding and all other steps to intensify the process. And we'll look at some modeling around a couple of these different functions. With that, I'm going to go back to the initial QB10 diagram that we were looking at here. So I pointed this out before, and it becomes increasingly important when we're talking about process intensification. With our jetted resins, especially the smaller bead jetted resins, we have excellent capacities at low resonance times. So if you reduce the bed height and flow very, very fast, you don't sacrifice much in capacity, and that's a function of course, the particle size of the bead, and also the superior mass transfer kinetics that you get from a jetted bead where there's more uniform like particle size distribution. So we can take advantage of that in a few different ways. We can simply just reduce the bed height and run everything faster. We can reduce the bed height and the diameter, and of course maybe run a little bit slower but increase some binding capacity. We can do a dual loading where we have faster non-loading steps, and sort of in conjunction with that, in a different sort of terminology, we can do what we often call dual flow loading, which would mean two different linear velocities during your loading phase. So you start loading very, very fast for a significant portion of your load, maybe 80%, and then the last 20% you slow down significantly to help maximize the binding capacity without suffering any breakthrough. And we'll look at some modeling examples of that in the next several slides. So let's start with the easiest one first. Let's just say we reduce the bed height. So I'm going to focus on the bottom line first here. So we're looking at competitor A, the predominant legacy resin. We're talking about a 60 by 20 column, 6-minute resonance time. You can see the other attributes here. Let's say that with our AP+50, where we have really good binding kinetics and really good binding capacity, we just reduce the bed height by half. So do a 60 by 10 and concomitantly reduce the resonance time by half. So we run twice as fast. You notice that we don't suffer any loss in capacity. We still have the exact same loss in capacity. We do need more cycles, but we still achieve it in the same total processing time because we're just running twice as fast. We have about the same buffer consumption. The cost, however, goes down dramatically, so we save 80% of cost just in the resin by reducing the size of the column. We get a 90% increase in productivity. There, if you do the math, you'll see that that's true. The productivity goes up from 13.5 to 25.9, and this will fit all the existing batch protocols. You won't have to change anything about that. But just by reducing the bed height and flowing faster, which is enabled by the size of the bead and our jetting technology, you can save 80% in resin cost and increase your productivity by 90%. Let's look at another one. It's a very similar example. So we have the two same size columns. So with the legacy resin, we got a 60 by 20. With our AP+50, we have a 60 by 10. But let's say instead of running twice as fast, we allow it to stay at the same residence time as the legacy resin to increase the capacity. So we've gone from, if you remember on the previous slide, we saw also around 51 grams per liter. We've now gone up to about 70 grams per liter by keeping the resonance time at 6 minutes. That does, of course, increase the total processing time, but we do decrease the number of cycles we need. So we've gone from 14 to 10. We've concomitantly reduced the amount of buffer that we need to achieve this, and we've still improved our productivity. So again, we see the same 80% reduction in the resin cost just by having a smaller column. We get a 24% increase in productivity, and we've actually reduced the amount of elution volume that's needed to achieve this separation. So we use less buffer. So if you have a lot of sustainability or environmental drivers in your processes, this resin can be uniquely suited to help address some of those, because we definitely can reduce buffer utilization and tank sizes in certain scenarios like this one. A third one here. We're still looking at a smaller column, but this one is sized a little bit differently. So we still have the 60 by 20 with the legacy resin, but here we've reduced the internal diameter and allowed the bed height to come up a little bit. So we got a 45 by 15, and we've increased the residence time even more to 10 minutes to get even more capacity out of this particular column. So we've gone to an 81.4 dBc. We have increased one cycle. The processing time is still a little bit higher, but here you can see we've driven down the cost of the resin even more. So 84% versus 80% in the previous examples. We've got a 39% increase in productivity and a 40% decrease in buffer usage. So again, we can both reduce cost of resins, increase productivity, and also decrease buffer usage to make these things more sustainable and more environmentally friendly, and of course more amenable to fast implementation with second-gen molecules and biosimilars. One last one here. There's a lot of modeling, I understand. So Now we're comparing AP plus 50 to AP plus 50 in this case. So we've gone to the short column. We got two 60 by 10 columns. But what we're doing is that dual loading strategy. So in one case, we're just loading at a residence time of 6 minutes. In the second case, we're doing a residence time of 6 minutes for the first 80% and then 10 minutes for the last 20%. So you can see here that we achieve a different dynamic binding capacity. In the 6-minute residence time, we still have an excellent binding capacity of 7 grams per liter. When we do the dual flow with the 6-minute coupled with the 10-minute, we can increase that to 81, almost 81 and a half. So we reduce the number of cycles that we need to achieve that separation because the binding capacity has gone up. We reduce the amount of buffer that we need. The processing time does go up a little bit, but the productivity does as well. So you can see we get a 79% increase in productivity and a 21% increase in buffer usage. So the ideas here between all these different modeling scenarios that I've been presenting here is that this resin, the AP plus 50 resin, is a very technically proficient and flexible resin in terms of achieving cost efficiencies and processing efficiencies. So you can do anything from as simple as just reduce the bed height and go faster to reduce these bed heights, do different variable loading strategies, and achieve a lot of process economics in lots of different ways to enable, faster implementation, better process economics, especially for a lot of the newer molecules that are coming out, especially around the Gen 2 and biosimilar markets. That being said, we're going to end up back where we were at the beginning. So hopefully I've impressed upon you very much that this resin is well suited to reduce costs. And not just reduce, as I said, not just reduce cost of the resin itself, which we are aiming to do, of course, but reduce costs in all aspects of your downstream process when it comes to buffer utilization, time, capacity, everything that we can think of. And of course, it's been designed to fit legacy and high-titer processes to the best of our capabilities. Technical equivalence, we showed that in a lot of the middle section slides where we showed that technically it performs just as well, if not better, as the legacy resins out on the market. And we have excellent capacity and resin lifetime to enable a lot of these high intensity strategies and high productivity models that we have. With that said, I have come to the end. I have a couple extra minutes, so I will happily field any questions that anyone might have. But I thank you very much for your time. It's been a pleasure to be here talking with you.